Let me introduce the speaker. Today's speaker is Leah Beneish. Is that how you say your name?
Beneish, yeah. It's
Beneish. Okay, she's coming to us from Montreal, and she's going to give a talk on Weierstrass modular forms and a dimension formula for certain vertex operator algebras. Okay, let's welcome her.
So thank you so much for the introduction and for inviting me to be at LSU today. Hopefully I'll be able to meet a bunch of you in person not too far from now. So this is a pretty big title. So I'm going to start by unpacking some of the words in the title. So Weierstrass modular forms are holomorphic parts of weight 0 harmonic Maass forms arising from elliptic curves. I'm going to explain more about how they arise from elliptic curves later. And vertex operator algebras, so VOAs for the rest of the time that I will write such a thing, are younger, spicier siblings of Lie algebras. And just in case anybody was wondering from this characterization of vertex operator algebras, no, I'm the oldest in my family. So a little bit of motivation. So VOAs are algebraic objects, but in the most basic way, you can think of them as complex vector spaces with a lot of extra structure. And they are used in conformal field theory and string theory. And they were given a formal mathematical definition in the 1980s. Okay, and this is by Borchard's gave mathematical definition of vertex algebra, and then Frankel, Lepowski, and Merman gave the definition of a vertex operator algebra. And this was in their work to construct the monstrous moonshine module. Okay, and then other properties that I need to mention about VOAs is that they admit a Z grading. Ooh, sorry. And we have modularity of their characters. This is work of Zhu, Dongli, Mason, and others. And an example of this, the most well-known example of this property, is with the monstrous moonshine module, be natural. Where the modular J invariant is known, well, I guess technically capital J, we subtract the constant term, is the graded dimension function of V natural. Okay, I told you the handwriting was going to get worse. Okay, so Van Ekeren, Moller, and Scheithauer give a formula for the dimension of a V1 space of certain VOAs. So I'm going to tell you the conditions on the VOAs later, but they're really natural conditions. And the reason the V1 space is of interest is, I'll say this again more specifically later, but the V1 space of a VOA in the C grading has the structure of a Lie algebra. And in the conditions for VOAs that I'm going to tell you about, it's been shown in many of the cases that the structure of the Lie algebra structure of the V1 space determines the VOA. So, but they give a dimension for this, or a dimension formula for this space. And they do this by expressing the character of the VOA explicitly in terms of the hop module for gamma naught of n. And this was, I think, published in 2018, but was on arXiv earlier than that. I will mention that they have a more general result now, but for the purpose of explaining my result with Michael, I will just explain this result because it's more clearly parallel. Okay, so today, in joint work with Michael Mertens, we extend the result to get a similar formula to the result of Van Ekeren, Moller, and Scheithauer formula in the case where x naught of, ooh, sorry, it moved. X naught of n has genus 1. So what's actually interesting / special about our formula is that this relates the theory of vertex operator algebras to certain invariants of modular curves. So this formula relates invariance of the modular curve x naught of n to the theory of vertex operator algebras. And as an application, we find a simpler dimension formula as a corollary of our main dimension formula that shows certain special values of the completed Weierstrass zeta function are rational. Okay. So I'm going to pause for some questions or thoughts or feelings.
Do you think it can be extended to other genus as well?
For the method that we use, the Weierstrass Mach modular forms, it really has to be genus 1 because, well, for now, since that's where we have just a simple pole at infinity for the Weierstrass Mach modular forms, which is what allows us to prove the theorem. But I'll explain more about that later. I think it's true it can be extended to other genuses with
okay,
just regular Mach modular forms.
Hyperelliptic cases, right? If they're,
yeah. So it can, but it won't be any more related to like these things. It's using the Weierstrass Mach modular forms allows us to relate it to arithmetic of the modular curve. So for higher genus, we could do it. It's just not clear whether the dimension formula itself would show the information from the modular curve. Like we could just use mock modular forms or some other kind of function to do this. But we don't know if it would be related to like I'll show in the dimension
All right, thank
formula.
you. Yeah.
Okay, so I'm going to talk now about Weierstrass mock modular forms. So harmonic Maass forms, I have to say first, are non-holomorphic. Sorry, this thing non-holomorphic generalizations of modular forms. And they have a natural decomposition into a holomorphic part. And a non-holomorphic part. Sorry, this thing is sensitive. So F equals F plus F minus. And F plus following Zagye is a mock modular form. And the non-holomorphic part, F minus, is related to a cusp form, and that's called the shadow of the mock modular form, F plus. And you get this shadow with, the Xi operator takes you from the space of harmonic Maass forms of weight k to cusp forms of weight 2 minus k. And if you have a cusp form, you can ask about what harmonic Maass forms are associated to that one. You get infinitely many because they can differ by a weakly holomorphic modular form. So one question is, are there canonical preimages under the Xi operator for, let's say, cusp forms associated to modular elliptic curves? And the answer in the case of Weierstrass mock modular forms is yes. So that's what they're kind of designed to be. So Weierstrass mock modular forms are corresponding canonically to cusp forms associated to modular elliptic curves. Okay, so now I'm going to actually define what they are. So let E over Q be an elliptic curve of conductor N. Let lambda E be the associated lattice. And then the field of elliptic functions with respect to lambda E is given by this C, P and P prime, where P is the Weierstrass P function. So here it is again, the Weierstrass P function in terms of W that are in the lattice. And if you take the negative antiderivative of the Weierstrass P function, you get the Weierstrass zeta function, which is this thing, and it's not elliptic, so that's not preserved under taking the antiderivative. Elliptic, did I spell it right? Yeah. But it can be completed to a function that is periodic with respect to the lattice, but it's not holomorphic anymore. Okay. So to tell you about the completion, I have to define something else, which is the completed Eisenstein series of weight 2, which looks like this. And then I'm going to also tell you that Fe of tau is in S2 of n. It's a new form of weight 2 associated to E. And phi sub E from x naught of n to C mod lambda E is the modular parameterization of E. So then the non-holomorphic function that is the completion of this Weierstrass zeta function is you subtract this completed Eisenstein series of weight 2 times Z, and then this Z bar term times the degree of the modular parameterization, and divided by 4 pi and the Peterson norm of Fe squared. Okay. So if the new form Fe of tau has expansion Ae of n q to the n, then the Eichler integral of Fe of tau is minus 2 pi I integrated from tau to infinity Fe of tau, or of t dt. And this thing will be n equals 1 to infinity Ae of n divided by n q to the n. Okay, so now I can finally define the Weierstrass Mach modular form. So now it's in terms of things we've seen before. So Ze of tau is zeta lambda E sub E of tau minus this completed weight 2 Eisenstein series times E sub E of tau. This is weight 0 and on gamma naught of n. And in general, Z E of tau has poles on the upper half plane, but this is not going to be the case for us in genus 1, which is why we like genus 1. So it's a result of alphas Griffin, Ono, and Rollin that there exists a meromorphic modular function ME for gamma naught of n such that the function Z hat E of tau, the completed Weierstrass Mach modular form, so now it's going to be a harmonic Maass form, is zeta hat lambda E sub E of tau minus ME of tau. And this ME is the same thing that if you subtracted it from the Mach modular form only, then that's what it would take for that Mach modular form to be holomorphic on the upper half plane. So then this is a harmonic Maass form. Of weight 0 for gamma naught of n. So it's actually an open question to figure out a closed formula for this ME of tau, as far as I know. But the conjecture is that the Weierstrass Mach modular form has poles whenever the E sub E of tau lies in the lattice. Okay. Any questions?
Isn't it the case that the Weierstrass zeta function is essentially the period function for the elliptic curve? I mean, I noticed that you took a period. See, the Eichler integral is a period for
Yes.
the cusp form. I'm trying to remember my Weierstrass theory. It's been many decades. It seems to me that it's introduced as a kind of antiderivative of the holomorphic differential, but it's regarded as a function of the tau as well as the z. So I'm wondering if this isn't related somehow to the period functions. So, this goes to Ling's first question about how would this generalize to higher genus, but there are analogs of Weierstrass zeta function to higher genus. These are called prime forms, but maybe we could talk about that later.
Okay, yeah, that sounds, I mean, we're going to see a lot of period integrals coming up in the constant terms of these mock modular forms later, but that would be really interesting if something can be done in higher genus that still has the arithmetic content showing up. So now I'm going to talk about vertex operator algebras. And it's a tradition to not ever define vertex operator algebra in a talk. So I will not break tradition, but I'm going to give an idea of vertex operator algebra. So a VOA is a complex vector space V. Equipped with two distinguished vectors. One and omega, called the vacuum vector and the conformal vector, and a map y from V to formal power series in Z and Z inverse with coefficients that are endomorphisms of V. So it assigns to each element a map, a formal power series. So V goes to YVZ, which is defined as sum over n and z of Vn, z to the minus n minus 1. And V, vacuum vector, conformal vector, and these operators have to satisfy many axioms. So one way to think about this is each vertex operator has infinitely many ways to multiply by V contained in it. So each one of these defines a different multiplication. And so having said that, the V1 space under certain conditions on the VOA has the structure of a VOA of a Lie algebra. So if V is of CFT type, just to be accurate there. And in that case, you take the V of 0 element from here, and that multiplied by something else in V, you define that to be your Lie bracket. Okay. And so there is a concept of V modules for a vertex operator algebra. And since I didn't properly define vertex operator algebra, I certainly can't properly define this, but a V module M is a vector space equipped with an operation Ym from V to and M Z inverse, and again satisfying axioms. Okay. And one more thing I have to say before I've said what I needed to say about these V modules is that you can also you can have the concept of twisted V modules if you twist by an automorphism G of the VOA. So an automorphism G of VOA V is a linear operator that preserves the vacuum vector and the conformal vector, and such that G times Y V Z G inverse is equal to Y G V Z for all V in V. And if G is a finite order, you can modify the axioms of V module to define G twisted V module. Okay. Any questions?
I have one question. So what's the point in keeping track of the Z and always in the definition of Y? I mean, is the variable Z change sometime or take on values, or is there any point to that? Or
Oh, so here, okay, well, so yeah, you can, so vertex operator algebras are like non-commutative and non-associative, but you can define, you can see in a sense that they're commutatives a little bit and associative a little bit. You can take different, like if you have something other than Z, if you have W and Z and you try to combine them, like if you write what you want it to be true for being commutative or being associative, and you ask that that each side is an expansion in a certain domain of the same function. So it's for that. I mean, but I only write Z here for being not adding too many messes.
thanks.
Okay, so going to introduce just a few more VOA conditions, but these are the conditions that I'm going to use for the theorem. So in the dimension formula, this is for V holomorphic, strongly rational vertex operator algebra of central charge 24. Those things I haven't said what they are. I can after, or I can not if it doesn't clarify things. But G is a cyclic group of automorphisms of V of order n. And V upper big G is the fixed point vertex operator subalgebra. And then V orb G is the orbifold VOA. It's just think of it as a direct sum of irreducible G twisted modules. So then the theorem of Van Ekeren, Moller, and Scheithauer. Let V orb G be as above. Remember that G was a cyclic group of order n. Then let n be such that x naught of n has genus 0. And then for cosmetic purposes only, I'm going to write n prime here. The theorem is not just for n prime, but I can't write the whole thing, and it looks better without. So we have the dim V1 plus dim V1 orb G equals 24 plus n plus 1 dim V1 G minus 24 over n minus 1 sum over k equals 1 to n minus 1 sum from I equals 1 to n minus 1 of sigma n minus k dim vg to the I k over n. So sigma of m equals the sum of the divisors of m. Okay, and then what did I want to say? Oh yeah, I wanted to say this might look a little bit strange to you, the sub k over n. In case it does, that's the k over n graded piece of dim v g to the I. So that this is a g to the I twisted v module. It has a grading too. And I told you we have a z grading, so I do in fact mean that, but I mean z grading can be like v n in z, and then it's n plus rho. Rho is some complex number or rational number, which is conjectured to always be positive in our cases. So that's why this is coming in. But yeah. Okay, and everything else is just pieces we know about. So the theorem that I have with Michael, it's the same idea. So let all these things be as before and be such that x naught of n has genus 1 and n is prime here, again, just for cosmetic purposes, but we don't even state the composite case in our introduction because it's really long and messy. So this is dim v1 plus dim v1 orb g equals minus ce n minus 1 plus n plus 1 dim v1g plus ce sum I equals 1 to n minus 1 k equals 1 to n minus 1 sigma n minus k dim v gi k over n. So let E be x naught of n, and then CE is going to be -3 minus the number of F2 points of x naught of n divided by 2 minus zeta hat lambda E. And this is why it's convenient that I have this iPad. LE1. So this looks a lot like the previous page. We have this term, which looks a lot like this term. And then there's n plus 1 dim v1 of g, which is also showing up here. And then this 24 over n minus 1 and 24, those are coming from the constant terms of the hot modulin. And then these are coming from the constant terms of the Weierstrass Mach modular forms. Okay. So the idea of the proof is for v in the normalizer, so not v, I want nu in the normalizer of gamma naught of n that commutes with all Heck operators TP with P does not divide n, then Z hat E hit with nu of tau equals zeta hat lambda E lambda little lambda nu E sub E of tau minus omega nu FE. Okay, I think I missed one. That should be right. So lambda nu is the eigenvalue of Fe under nu, and omega nu of Fe is this period integral minus nu, this is a nu inverse infinity, Fe of tau, no, not tau, t dt, have it. And then note that if nu is the Ekeren involution, then omega sub Wn equals LFE1. So we use this result because we're expressing, which I'll explain in a minute, the character of Vg as a modular function of level n. We're expressing it in terms of these Weierstrass Mach modular forms. And so that requires canceling out all of the poles at each of the cusps. So we look at the expansion each of the cusps, which is why we needed to be able to apply Ekeren involution. And this is where the constant term shows up. I'll explain how we actually see that. But first, so our dimension formula proof also relies on a result that we prove that for n in these in this set, then roughly you can express any harmonic Maass form of level n in terms of the Weierstrass, the completed Weierstrass Mach modular form and their images under Ekeren involutions and Heck operators. So this is theorem 1.4 of our paper. So this result says, so this is theorem 1.4. One can express any harmonic Maass form of level n in terms of the completed Weierstrass Mach modular form for level n and their images under Ekeren involutions and Heck operators. So finally, we use the fact that the character of Vg is a modular function for gamma of n without poles in the upper half plane. And we know how the character Vg of tau behaves under transformations. And using the theorem that I stated just in the last slide, this one, well, okay, I didn't properly state the theorem, but the theorem I told you about, we express character Vg of tau in terms of Weierstrass Mach modular forms using theorem 1.4. And then what's left is the constant terms, and that's where these this L value of Fe at 1 is showing up in the formula. Okay, so it's hard to pay attention for a long time in Zoom talks, and I'm almost done, but I want to tell you about this rationality result. So I wanted to give everybody a little break So the break is not, I mean, you can leave if you want to, but the break is, if you have a volume, or if you have volume all the way up, I suggest you turn it a little bit down if it's in your ears or something. So this is why. And I mean it about the volume. I guess you can see what's coming. Let's see if it works. Sorry, out of practice. Okay, so now that everybody's refreshed or startled, I'm gonna go into the rationality result. Okay, so to our knowledge, mine and Michael Mertens, the rationality of zeta hat, the completed Weierstrass zeta function, hasn't been evaluated at L function at value at 1, has not been investigated so far. But it is a classical result. Okay. Of Schneider that the value of the uncompleted zeta function, zeta lambda LE1, is transcendental. So we have a corollary to our dimension formula theorem. So this is assuming all of the conditions of the theorem. Okay. For P prime, this time I really mean P as prime, and x naught of P is genus 1. If we have the sum from I equals 1 to P minus 1, sum from K equals 1 to P minus 1, sigma P minus K, dim VGI, K over P. If this is not equal to P minus 1, for some VOA V satisfying the conditions of the theorem, then zeta hat lambda E, that doesn't even look like lambda, lambda E LE1 is rational. And so for P equals 11, 17, and 19, we find that zeta hat lambda E LE1 equals 17/5, 2 4/3, 4/3, respectively. And Moller and Scheithauer said that they actually found suitable VOAs such that according to this corollary, these things should be rational. So, thank you.
Thank you.
Okay, thanks. Are there any questions for our speaker?
So the rational number you find is numerically, or it's
Yeah, it's numerically.
Do you have a control for the denominator?
Do you mean in general, or I mean in this specific? Okay.
Say just for those cases, like if you claim that it's a proof, one thing you can do is if you know the denominator is within certain range, right? The error term is so small that you know that must be the corresponding value.
Yeah. Well, so the corollary is it's just saying that the value should be rational. So that those values were computed numerically, but I don't know if we have control over. If we know something more about the denominator, you're right, then we could say that those are provably the values, but I don't know.
Yeah, the result looks kind of interesting. It says if there exists one VOA satisfy this condition. So does it also mean that for all the VOA, the same condition will be true, or the assumption itself is kind of interesting. Right? It's the existence of something.
Yeah, it's weird.
And can you say once you know one VOA, if you plug into the formula, it's not the same as P minus. That for any other VOA, if you plug that into the formula, they are all, satisfying the same or the behave similarly.
Are you asking if you plug in if you have a VOA that?
You said that if there is a VOA.
Yeah. Yeah. So if you find one, then the dimension formula in the theorem is supposed to hold for all VOAs that satisfy this property. So if you find one such that this is not permanent, such that this is not true, then you know basically like you end up with one side of the equation is something rational, and then you're left with this thing. So you do only need one example.
Okay, all right. Thank you.
So you don't have more example. Can you go to the next page? So these three are the numerical result that you have, right?
Yes.
So it looks like it's the rational number is getting smaller. Is that true?
I don't know. It's not enough data for me to to
so
draw a
do you
conclusion.
think there will exist other primes so that you find rational value? Do you expect that?
Actually, that's a really interesting question. I think I need to understand a lot more about these period integrals to be able to say that, but I do think that something else might be true. Like, for instance, in the composite level formula, we have other omegas showing up, and I don't know, there might be something we can say there, but I don't know yet.
Yeah, maybe if there exists infinitely many things, you can try to say if this converges to one. I don't know.
Yeah, that would be interesting.
For this cases, the denominator does look like they are divisors of P minus 1.
Yes.
Oh, that's true. Yeah.
But looking at 3 examples, probably it's not enough evidence.
Is there another question?
Can I ask a question? So is there a way, like connection, like the link to get mock theta functions and Weierstrass mock modular forms?
Sorry, I couldn't hear very well.
I think he was saying mock theta functions. Is that right?
Yeah, mock theta
Mock
functions.
theta functions. Is that what you were saying?
Yeah, mock theta functions, Ramanujan mock theta functions, and Weierstrass mock modular forms.
His connection is kind of bad. I think you're asking, is there a connection between Weierstrass mock modular forms and these theta functions? Is that right?
Yes.
This I'm not sure.
Okay.
I think that
might be a stupid question. I'm sorry.
No. I think you can do you can prove the same theorem for any, pretty much without restrictions on the level, if you allow yourself to use harmonic Maass forms or mock modular forms with just a simple pole and infinity. But then the problem is, it's not a problem. It's just, it wasn't the purpose of this project. The thing is that these Weierstrass mock modular forms had interesting constant terms with this showing up. And in those cases, I don't know what the constant term will look like, but you could certainly prove something with more general mock modular forms. So in that sense, I don't know.
Okay. Okay, thanks.
Anybody else? Well, just one final thought. The Weierstrass zeta function is the antiderivative of the Weierstrass p function.
Mm-hmm.
So it is indeed a period. Well, it's the indefinite integral, if you will, of the Weierstrass p function.
Mm-hmm.
And there are, in higher genus, people have analogs of these things. I think they're called prime forms and other kinds of fancy stuff, which I actually don't know about. But it might be interesting to look at this for the hyperelliptic situation, because one has a rather explicit theory there, which I'm not real familiar with. But I think these things have been generalized by various people. And of course, there are modular curves of genus 2.
Yes.
So I don't know where it goes, but that's just tossing my hat into the ring, you know.
No, that's a great idea. I think that for us to do it was the obstruction was the relationship through these Weierstrass mock modular forms is really the main tool we're using. And in genus 1, that's when you have only a simple pole at infinity for these mock modular forms. And in general, you have poles in the upper half plane, and you have to subtract this meromorphic function for which there's no closed formula yet. So that's it. Like that's the challenge. But if there's another way around it that uses these.
Well, when you go to higher genus, one of the key tools you use is theta functions. It's just what Shashika was mentioning. You know, you don't have a Weierstrass theory in this shape, but you do have a theory of theta functions that generalizes to all genus. So I don't know where it goes. So that's
a great idea.
Any other questions for our speaker? Well, if not, let's thank her.
Thank you.
Thank you.
Well, okay, that's it for today, and thank you for the talk. And I guess bye-bye.
Bye. See you next semester.